we are discussing the forward Kolmogorov equation for a special case of continuous time Markov chain, that is a birth-death process. For a birth-death process, the Q matrix is a tridiagonal matrix. Therefore, you will have the equations from the forward Kolmogorov equation. You will have only two terms in the right hand side for the first equation, and you will have only three terms, the diagonal element and two off diagonal elements. Therefore, the second equation one can, the first equation one can discuss first. The p dash of I comma 0, that is nothing but the system is not moved from the state 0. Moving from the state 0, that rate is lambda naught, therefore not moving minus lambda naught times the probability, and or the system can come from the state 1 with the rate mu 1, therefore mu 1 times p I comma 1 of t. For all other equations, either the system comes from the previous state with the rate lambda j minus 1, or it comes from the forward one state with the rate mu j plus 1, or not moving anywhere. So, these are all possibilities. Therefore, with these three possibilities you have three terms in the right hand side, and that is the net rate for any state j. So, if you solve this equation with this initial condition Kronecker delta I comma j, you will have the solution of a p I comma j. Here I am discussing the steady state distribution. The way I have discussed the limiting distribution, that is a limit t tends to infinity, probability of I comma j of t exists, then it is called the limiting distribution, and the stationary distribution is nothing but for the DTMC it is a pi p is equal to p summation of pi a is equal to 1, for the CTMC it is pi q is equal to 0 and the summation of pi I is equal to 1. That is going to be the steady state distribution, stationary distribution. Now, I am discussing the steady state distribution, that is nothing but when t tends to infinity, the birth-death process may reach steady state or equilibrium condition. That means, the state probabilities does not depend on time. That is the meaning of a steady state distribution. As a t tends to infinity, whenever we say the birth-death process reaches a steady state or equilibrium, that state probability does not depend on time. That means, if a steady state solution exists, since the state probabilities does not depend on time t, the derivative of the time dependent state probability at time t, that derivative at t tends to infinity becomes 0 if the steady state solution exists. Since the state probabilities does not depend on time t as a t tends to infinity, I can write as a pi I is limit t tends to infinity of pi I of t. So, this is different from the way we discussed earlier, that conditional probability p I j of t. But using p I j of t, one can find out what is pi I of t. That is nothing but the pi I of t that I have given in the first lecture for the CTMC. The pi I of t, that is nothing but what is the probability that the system will be in the state I at time t. That is same as what is the probability that the system will be in the state I given that it was in the state some k at time 0 multiplied by what is the probability that it was in the state k at time 0. That is nothing but summation of k, and this is nothing but the transition probability, and this is nothing but the initial probability vector element. So, using pki of t or pij of t, that is a conditional probability, one can get the unconditional probability. This is nothing but the distribution of x of t. So, this is a probability mass function, probability mass at state I. So, now what I am defining, whenever the steady state distribution exists, that means it is independent of time t. Therefore, as a t tends to infinity, the pi I of t can be written as the pi I. and whenever the steady state solution exists, I can use a limit t tends to infinity, the derivative of a pi I of t, that is going to be 0. Therefore, I am going to use these two to get the steady state probabilities for the birth death process. Since as a t tends to infinity, the derivative of pi aj of t is equal to 0, therefore, all the left hand side in the forward Kolmogorov equation, that is going to be 0. The right hand side you will have as a t tends to infinity, the pi I of t, that can be written as the pi 0 and the pi 1. So, the way we write the conditional probability for Pij with the Kolmogorov forward equation, you can write the similar equation for the unconditional probability pi i's also. So, now I am putting the left hand side zeros because of this condition, limit t tends to infinity, the derivative is equal to 0, and the right hand side I am using as a t tends to infinity, this probability is nothing but the pi i's, therefore, it is going to be minus lambda naught times pi naught plus mu 1 times pi 1, and all other equation has 3 terms, and this is a homogeneous equation, and you need a one normalizing condition. So, from this homogeneous equation I can get recursively pi i's in terms of pi naught. So, from the first equation I can get a pi 1 in terms of pi naught, and the second equation I can get a pi 2 in terms of first pi 1, then I can get a pi 1 in terms of pi naught. Therefore, recursively I can get a pi i's in terms of pi naught for all I greater than or equal to 1. Now, I can use the normalizing condition, summation of pi I is equal to 1, therefore, I will get a pi naught is equal to 1 divided by summation of this many terms in the product form. Since we need a steady state probabilities and all the pi i's are in terms of pi naught, as long as the denominator is converges, you will have a pi 0 is greater than 0. Once pi 0 is greater than 0, then we will get all the pi i's with the summation of pi is equal to 1. So, whenever this series converges, then I will have a steady state distribution with the positive probability, and the summation of probability is going to be 1. So, this is the condition for a steady state distribution for a birth death process, because we started with the birth death process forward Kolmogorov equation. Using these two conditions, we have simplified into this form and use the normalizing condition and get the pi naught. As long as the summation is or the series is converges, then we will have the steady state. If the series diverges, that means by substituting the values for the lambda i's and mu i's, and if the series denominator series diverges, then the pi naught is going to be 0. In turn, all the pi i's are is equal to 0. Therefore, the steady state distribution won't exist if the denominator series diverges. I am going to give one simple result for a irreducible positive recurrent time homogeneous CTMC. We know that a limiting distribution exists, a stationary distribution exists. Now, I am including the steady state distribution also exists. I have given for a steady state distribution for the birth death process, not for the CTMC, but here I am giving the result for the CTMC. All the three distributions exist and all are going to be same. Whenever the CTMC is a time homogeneous, irreducible, positive recurrent, all these three distributions are same, and one can evaluate, one can solve these two equations. Pi q is equal to 0 and with the summation of pi a is equal to 1, you can get the limiting distribution, stationary distribution, or steady state or equilibrium distribution. As a special case of birth death process, I am going to discuss these two processes in this lecture. Whenever we say the birth death process is a pure birth process, that means all the death rates are going to be 0. We started with the birth death process with the only lambda i's are greater than 0 and the mu i's are going to be 0, then it is going to be called as a pure birth process. There is a one special case of pure birth process with the lambda i's are going to be constant, that is lambda that is a Poisson process that I am going to discuss in the next lecture. And in this pure birth process, these lambda i's are the function of I. Here all the states are transient states. Here I am discussing the pure death process. A birth death process is said to be a pure death process if the birth rates are 0 and the death rates are non-zero. In particular, we shall obtain the time dependent probabilities of a pure death process in which the death rates mu i's are equal to I times mu. As I given the example as a fourth example in the birth death process, this state 0 is a observing barrier. Therefore, the state 0 is a observing state and all other states are going to be transient state. And here the limiting distribution exists, and one can also find the time dependent probabilities for this model. Suppose you start with the assumption the system at time 0 in the system is in the state n. At time 0 the system is in the state n at time 0. With that assumption, I can frame the equation, that is a pi n dash of t is equal to minus n times mu of pi n of t. That means the rate in which the system is in the state n, that is nothing but not moving to the state n minus 1 with the rate n minus n times mu. Therefore, the equation for the state n, that is a pi n dash of t, that is equal to not moving from the state n, therefore minus that outgoing rate, that is n times mu, being in the state is n, therefore pi n of t. I can use the initial condition pi n of 0 is equal to 1. So, I will get pi n of t. For the second equation, I have to go for what is the equation for the state n minus 1. So, the pi n minus 1 dash t, that is nothing but either the system come from the state n or not moving from the state n minus 1. Therefore, system coming from the state n, that is a n mu times the system being in the state n minus n minus 1 times mu pi n minus 1 of t. So, we will have a two terms in the right hand side coming from the one forward state or not moving from the same state. So, we will have two terms for j is equal to 1 to n minus 1. For the last state, that is the state 0, the systems come from the state 1. Since the state 0 is observing states, there is no second term. So, it is going to be mu times pi n of t. So, you know pi n of t, use the pi n of t in the equation for n minus 1 and get the pi n minus 1. Like that you find out till pi 1, use the pi 1 to get the pi 0 of t, use the recursive way. So, using the recursive way, you will get the pi j of t is equal to n c j combination n c j and e power minus mu times t power j. This is a survivable probability of system being in the state, and 1 minus e power minus mu of t n minus j. Suppose the system being in the state j, that means from the state n this many combination would have come, and the survivable probability is e power minus mu times t, and that power. So, this is nothing but the probability p power j and 1 minus p power n minus j. Therefore, this pi j follows a binomial distribution with the survivable probability e power minus mu t being in the state j. So, for the pure death process, I have explained the time dependent probabilities of being in the state j, that is unconditional probability. So, with this the summary of this lecture is I have discussed the limiting, stationary and steady state distributions. I have introduced a birth death process, some important results also discussed, and at the end I have discussed the pure birth and pure death processes also. In the next lecture, I am going to explain the important pure birth process, that is a Poisson process. Thanks.